It's been a while since I did a video geared towards college students, but I was doing Advent of Code 2015 and I came across this gem, some assembly required. And I thought it would be fun if we did this one together. So if you're graduating from college, you should have all of the requisite skills to solve this on your own. I thought it would be fun if you could do this one together. Um, you can read this sort of vignette on your own. It's got a Bobby Tables reference. It's pretty funny, but I'll give you the gist of the problem. The gist of the problem is you're given a list of assembly instructions, and these instructions map an expression to some output variable, and then it asks you the value of one particular output variable. And the gimmick here is that to get the value of an output variable, you have to evaluate the expression. And the expression might reference other variables, which you also have to evaluate. So, for example, this one, which is x or y output to e, you would need to know the value of y and x to get the output for e. And essentially, we're doing bitwise and over two integers here. We also have operators or, left shift, right shift, not. You get the gist. So let's see. I've done this one before in a different language, and at that time, the solution I used, I mapped all the output variable to their expressions, and then we just did some recursion. So let's do that in. Let's do Zig. So what version of Zig do I have exactly? I'm doing master branch. This is post 0.15. So we should have like the new writer, new reader, that sort of thing. First thing, let's get our input. Get our puzzle input. So you can see there's quite a bit of instructions here. About 340 instructions total. Very good. And let's do a Zig file. Let's do solution.zig. And we're going from scratch here. So let's do const std. And while I'm writing some of this boilerplate, I guess I can talk about some of the things going on in my life. Very recently, I did get in touch with some folks from University of Houston, and something pretty strange happened. I had some people requesting, hey, could you help me get a job? Could you give me some reference? And they were appealing sort of to a common culture that common background culture that we might have, or maybe they were appealing to a common skin pigment that we might have. And of course that's already sus somewhat, but my response to everyone who maybe asks for these sort of things is, okay, well, show me your resume. I have to be, if I'm going to recommend you, it's probably going to be on the basis of something. So I asked them, hey, do you have a resume I can look at? And what I found was that the resume had maybe 2 or 3 programming languages and a reference to a job at McDonald's that they had. And there's a saying. I think it was Mos Def who said this back when Eminem was first coming on the scene. But the saying, it goes like, real recognizes real. Like, if I see that you're not, all you have is some coursework and a job from before you started school, like, I'm not seeing passion there. I'm not really convinced that you really want to be a software engineer. And for that reason, I told him no. And and my advice to anyone who's looking for sort of, if you're looking for somebody to to vouch for you, you have to give them a reason to vouch for you. Like, you can't just ask for, you know, someone to back you up without anything. I don't know what to say, man. That guy could have done a better job. Like, here's the thing. One of the things you can do is show me you're interested by having some personal projects. Things that you're doing without necessarily requiring people to tell you what to do. Like, if you have personal projects, it shows that you're actually super passionate. And he didn't have any personal projects, and I just found that to be like weird. Like, dude, are you sure you want to do this for the rest of your life? Like, this is going to be the next 30 or 40 years of your life. So I mean, if you're going for software engineering, definitely have a resume that's fleshed out. Really, at your stage, you should have 3 sections: one for internships, one for personal projects, and one for coursework. Like, if you have those 3, you're already showing tons of passion. And passion is not the only thing people look for, of course. So, there's other things as well. So let's do 1024. This is just a buffer. The new thing is that the interfaces to readers and writer in Zig have a buffer, like a ring buffer, included in there. So I think we needed to provide a buffer before too, but in different fashion maybe. So in this case, I'm putting a buffer right in here. Buffer. And then we need the reader interface. So we can do file reader dot interface. So let me back up here. Let's see, what are the things that people look for in a resume? They look for passion, they look for competence, and they look for coachability. In other words, teamwork, basically. And if you don't have those things, you got to get them. And the McDonald's job, by the way, is nothing to scoff at. That does show teamwork. But what I also need to see is passion, meaning your personal projects. You're actually pursuing this stuff outside of schoolwork. And I also need to see coachability, right? Coachability, teamwork. Well, I already mentioned the coachability. Competence. I need to see competence. And one really good way to get all 3 of those things is, to be honest, you do need to have internships, because that shows all 3 of those things all at once. And you get paid for doing that too. So you've already shown that you're professional. You're out there. And I'll introduce you now to the rule of 3. The rule of 3 is, if you have one internship, you are now a candidate. Wherever you apply, your people are gonna look at your resume seriously. If you have 2 internships, you're now a competitor. You're not just a candidate that people will consider, but a candidate that people might want, and that might even beat out the competition. And if you have 3 internships, at that point you're a shoo-in. Like, honest to God, there's no reason why you can't have whatever job you want, including like in a FANG company. Like, you should be able to apply to a FANG company and get a job. So definitely think about that. Make sure you flesh out your resume. You should have been fleshing out your resume throughout your entire coursework. But at this juncture, like, if you're getting ready to apply to jobs, you should have had those internships already. But if you don't have them, apply like mad. Go to every single career fair. If you're starting from scratch, Oh, I'm gonna forget to flush the buffer. Okay, let me just do that here. Okay, very good, very good. And then we'll do function solve. And this one is gonna have a reader and a writer. Reader and a writer. Yeah, you should be going to every single career fair that's on offer from your university. Every single one, without fail. Well, let's do bang void here. Okay, so in Zig, this bang means that this thing might return an error. So, and try means, hey, try it, but if you have an error, just go ahead and throw that error and handle it upstream. And in my case, the way main handles it is that it will, print out the error and it will panic, basically. It'll print out the error, print out the stack trace, and then just straight up panic. And that's sort of what I want. Unused function parameter. Okay, sure, whatever. Let's find this one. Okay, so let's go back. To the vignette here. And what do we need? Let's start by codifying some of these concepts. So we have expressions, we have an operator, we have operands, we have these keys. Let's see. Okay, let's go here. Okay, so what are keys? Keys are essentially 2 bytes. They're 2 bytes, just interpreted as characters. And then what are operands? Let's do const operand. And an operand is either, it could either be a label. I mean, it could either be this variable or it could be a number, right? It could be either one of those things. And the nice thing about Zig is it lets you interpret the same memory slot in different ways using tagged unions. So let's do union enum. And this will be either a U16. It's either going to be a U16. So if we come back here, you can see that it says it should be in this range. This is a 16-bit number, right? So so let's call this num U16. Okay, so this is also 2 bytes, and it could either be that 16-bit number or it could be a key, which is 2 characters, right? So these are both the exact same size in memory. So this is a nice one. Okay. Let's see, what else do we have? What other concepts can we do? We can also do operators. Which is an enum. And what operators do we have? We have assign. We have not. These are 2 unary operators. We also have or and left shift, and right shift. And you guys should know the difference between binary and unary operators, just to give you sort of I guess, taste for that. Here's not. That's a unary operator, meaning it operates on just one operand. A binary operator like AND will operate on two operands, right? So assign and not are unary. Everything else is sort of binary. All right, very good. We also have this idea of an expression, and we'll have that be a struct. And expressions have a few qualities. Expressions have an operator, okay? So there's an operator, and they have at most 2 operands. So there's a left-hand side and a right-hand side. And eventually, initially, those expressions are not evaluated, But once they're evaluated, they're actually going to have a 16-bit integer value. So let's also codify that in U16, and this is going to be an optional in Zig. This question mark means that it could be null or some value. And in my case, we're going to start things off as null. And that's your expression. Okay. Very good. What is next? I think let's also come on down here. Oh, come on down here, and let's just do the high-level code. Like, what are we trying to get out here? And initially, we're just going to have a hash map. Then we're going to read each expression, use that expression to populate that hash map, and then evaluate recursively. All right, that's going to be our way of doing things here. Initializing the map. Okay, so let's do var lookup is equal to map. And this is an auto hash map. So if you look at the code from before, this is just, I'm aliasing an auto hash map. And in this case, I'm mapping keys to expressions. And then we'll init that with our allocator. And then we want to defer the cleanup. That's another nice thing about Zig, is that we can defer our cleanup and things just sort of work. So how do we want to read this? So let's do true. While true, we are gonna iterate. And then from our reader, we're gonna read all the way till the end of the line. Take delimiter inclusive, I think is the name. I think that's the name. Let me just make sure. Returns a slice of the next bytes of buffer data from stream until the delimiter. And the delimiter is a U8. It's a U8, so it's going to be single quotes. And then if we catch it, let me just double check here. Go to definition. Looks like there's a delimiter error. I think this is going to throw an end of stream error if it needs to. So in our case, what I'm just going to do is I'm going to catch. And if we catch any error, let's just assume it's end of stream, and we're going to break, right? This is not a production code base. We can sort of, you can sort of take liberties. Okay, I'm running out of typing space. I want to be able to see this stuff. Okay, so now we have our line that we've read, and I want to trim that line down. I want to get rid of, because it's saying inclusive. I'm taking all of the bytes, including this new line byte probably. So I'm going to trim this down to I want this to be in bytes. This is what I'm trimming down, and in particular, I want to get rid of this new line completely. Yeah. And now what do we want to do? Now that we have the line, we're going to write a function called parse line and populate lookup. And here we're going to send in our line, and then we're going to send in as a reference our lookup table. And the idea is that with each of these lines, we'll parse the line, and then we'll get the key out of it, and then this will be our expression. And we'll map this key to the expression. And we'll do that for every single line. And now, by the time we're done with that, what's this error? Let me escape here. Expected. Okay. Let's do that. Okay. And now, our map should have everything in there, right? It should be good to go. So we should just be able to just pull out the value, and which should be a U16. Evaluate key. Wait, is this thing going to throw an error? Do I anticipate any errors being thrown? I don't think there should be any. I'm just getting things from the thing, right? There shouldn't be any errors. But anyways, it should take a key as a parameter, and So here's the thing, right? A key can be a single character, or it can be, two characters. And our key, our sort of, key is 2 bytes. And in the case of a single character key, I want a padding byte that is consistent. And I guess for this one, we'll just use @. The reason this has to be consistent is because we're going to be hashing it. We're going to be hashing it, and I want the hash value to be predictable, right? So this will be the second byte, and that'll be the placeholder byte in case we have a single character key. And we're also going to send in the lookup, okay? That's our high-level code for this particular thing. And then, of course, we will print out our answer to standard out. And what is this going to be? This is going to be value. Okay, very good. So that's our high-level code. That's sort of it. Okay, of course, I haven't defined these functions yet. All right, so but you get the idea. You get the idea. Like we're gonna parse the whole file, add it to the lookup table, and then evaluate the key, and this will be our recursive call. And this should give us sort of what we need, right? All right, very cool. Let's go back up here, and let's start defining these higher level functions, okay? So let's do fun parse line and populate lookup. Was that the name of the populate lookup? I think so. And this, I believe, took in a line. So that'll just be some characters. And it sort of outputted, it populated a lookup table. So this will be the lookup, and this will be a pointer to a map of key expression. Okay, that was the signature for this one. And then we also had another function, which was evaluate key, and that took a key of type key, and it also took a lookup, a reference to a lookup. So let's do map key expression. Okay, so this is our high level. And we want to try and implement these things. Should I start with parsing, or should I start with evaluate? I'm not sure. I think we should start with parsing. It's the first thing on the list, right? Parse line and populate lookup. Okay, let's do it. Actually, no, let's not do it. Okay, so I've solved this problem before, and I know that this function can get super gnarly unless we do some work. We got to do some low-level work, and in particular, we need some helper functions. So the first one is key, and we're gonna take in a string. And we're gonna output a Boolean, which tells us, hey, is this a letter? Is this a variable? Or is this a number, right? Like, that's really what we want to know. And, we can do that pretty simply by just, iterating over that and, pulling the characters. And then we should be able to do if is lower, if the character is a lowercase letter, then we know, actually we don't really need these brackets, do we? Then we know this is a sort of a variable. Otherwise, we know it's not a variable. It's not a key that we need to address. Okay, what else do we need? Okay, we did is key. What about as key? As key means we've already determined that this is a key, and we would now like to parse it into an operand. right? Like that's what this function will do. And let's think about this. We need a buffer of 2 bytes, right? So a buffer would be something like this, and buffer of 2 bytes. Okay, so undefined, it will allocate that buffer, not allocate, but it will find 2 bytes for us somewhere, and var will let us overwrite those bytes. Initially, we won't know what bytes are in there, right? It's probably just junk. So first, we're gonna have to trim, because I think, like for this one, for example, I'm gonna try and send in maybe everything after the or, and it might have a space in it, and I don't want to have to deal with spaces. So let's trim that key. We'll go const s is equal to trim. We're dealing with bytes. We're gonna take this underscore s, and the bytes we want to trim are space, new lines, carriage returns, that sort of thing. Okay, so that should trim everything down, and then we can sort of say, what goes into our buffer. So in the first or the 0th index of our buffer, we'll take the 0th index of the string, right? So like we should have at least 1 character in the string by the end of the trimming. And the second is, what about the second character? Now, in the case that this is a 1 character label, right? In the case that it's a 1 character label, we could just do, s sub index 1, right? S sub 1. But in the case where it's in the case where it's 2, we can do s sub 1. But in the case where it's 1, we want to put in our filler, our filler byte, which is the @ sign in ASCII. I think we can just use a ternary here. So if, let's say, s.len is greater than 1, we'll do s1. Else, we'll just hard code this @ here. And then, what are we returning? We're returning an operand. So we can, Zig will infer that this is an operand, and we'll populate the key with our buffer. And I think that's it, right? What's this error in here? Nope, no error. Okay, great, we got ASCII. Now what about its cousin, as int? Okay, here this is gonna be, I think I'm gonna have to trim this one too. And because we're using parse int for this one, I might have to bubble up an error. So let's do const s for trimming a byte, and it's gonna be, I should have just copy pasted the line, to be honest. And in this case, we have a helper method. We can use parse int, and parse int says, hey, what are you giving me, or what do you want back? I think, and then what we want back is a u16. Buffer is gonna be whatever s. Buffer is s, right? Buffer is s, and then the base is 10. So we want a decimal character back. Okay, awesome. I think that's it, actually. But we have to return an operand. You know what? I'm gonna do another as int literal. Does that make any sense? Yeah, I want to do another one. I want to do another function for that, because I might want to actually just set something to a literal, and I want that ability, to be honest. And it's gonna be u16. And what are we returning? An operand. And here we're just returning an operand. Of course, Zig is helping us with the Zig is going to help us with the, man, going on here? Okay, very good. That was me. That was me. It's not zig. It's num. Num is equal to n, and then we'll just do a semicolon, and that is essentially an operand. That's returning us an operand. And also, of course, it's not just a key or an int, but we could have a situation where it's both. It could be both. It could be an int or a key. So we'll do an as any, and this is going to take an s, a string. So we're going to give it a slice of bytes, and it's going to return us an operand. And oh guys, this is gonna look beautiful. Okay, if we're gonna do ternary operator, if is key s, then we're gonna return as key s, else I'm gonna try to return it as an int. Isn't that beautiful? I think that is. That's gorgeous. What's this error? No error. Okay, awesome, beautiful. Mwah. Okay, done. Okay, we did the work here for the low level stuff, and that means now that we can go on to the high level stuff, it's going to be a much more pleasurable experience. That's what I'm hoping, anyways. So let's come on down here and let's find the close bracket, and yeah, find close bracket and go into insert mode. Okay, awesome. Okay, so what are we trying to do at this point? Okay, this is supposed to parse the line and populate our lookup map, right? So what do we need from this line? Okay, that's what the question we have to ask. So we need a key, which is going to be a key, and we're going to set that to undefined. We're going to need an operator. We're going to need the left-hand side value first. That's an operand. And then we're going to need the right-hand side, which is also an operand. Okay, that's what we're going to need from sort of this thing. And now that these equal signs are lining up, this seems wrong not to do this. Okay, so that's what we're going to need. And then essentially what we're going to be doing is we're going to do const expr, which is going to be an expression. And this is going to be some struct where the key will not the key, but the operator will equal the operator. The left-hand side will equal left-hand side. Right-hand side will equal right-hand side. Okay, and then we're gonna put this in the lookup. Right? We're gonna put this in the lookup. That's the whole thing. Lookup.put key expression. That's the whole thing. Okay, and this is going to be a let's go to insert mode, bang void. This is going to be a bang void. Okay, so this is what we're trying to accomplish in this sort of in this method, and the line is supposed to provide these values for us. So how do we go about doing that? Well, there is something called split sequence. I think std.mem split sequence. And let me see if I can just go to definition here. This will let us split on some delimiter. And what it gives us is a view into the underlying buffer. Split sequence does not create any new memory. It just gives you a view into the already existing memory. And then you can iterate over those views. And you can see it's iterating over those views here. And when it returns null, I assume that means this is for, this is giving you an iterator. Yeah, this is giving you an iterator. Okay. All right, so this is what we're going to use. That's what we're going to use, std.mem split sequence. And let's get an iterator out of this. And do we want this to be a var iterator? Let's just do var just in case. And comp time type. Comp time type. What comp time type are you referring to, sir? Are you talking about the buffer? I think they're just talking about the buffer here. So it's a byte, right? It's just a byte. And then it's going to be the line that we have sent in, and then the delimiter. Okay, let's come over here for a second. The delimiter is going to be, let's see, a space dash space. Okay, that's going to be our delimiter, and the iterator will give us the expression first, and then it will give us a key. Okay, so that's what I'm expecting to happen. So for all cases, it'll do expression first, and then it'll give us a key. So that's what we're gonna do. Space dash greater than space. Okay, very good. So we have our iterator, and now we should be able to do something like this. While iterator.next, and then we can capture the section. Do we want to trim this one as well? I think we should, right? Just for posterity. Okay, let's trim this one as well, just in case. Like I don't want to run this thing and run into bugs and stuff like that. So we're trimming this again. We're gonna do U8. I'm gonna give it the whatever we captured, and then I'm doing way too much trimming. I think we can do without the trimming, but I'm just gonna keep it in there. Okay, so right now let's focus on parsing out the expression, and then we'll parse out the key. Okay, so let's start with the expression. Let's see if am I still recording? I think I am. Okay, so the expression is going to be, what's the first thing we need? We need an operator, right? Operator. Okay, so can we do op is equal to then do a whole bunch of if else's? That seems really slimy. Let's just do it right. Okay, so I know from past experience where there is an assignment that's a let's see, $? Is $? Yeah, so there's an assignment that happens to be a variable, right? So this is a pretty short one. This is just 2 characters. So if I say this section, if I come back over here and I say section dot len is less than 3, I should be able to say this is an assign operator. Oh yeah, what's going on here? Okay, I should be able to say this is operator is an assign operator, and again, Zig will infer. And then else if, what's next? There's a not operator too, right? So let's come over here again, and then this time we'll search for not, and I can see that like this is all starts with a capital N, right? So I should just be able to do this. It's an N byte, right? So equal this, and that'll tell me if it's a not. I think so. I don't see why not. Okay, sorry. Else if next one I think is or. So let's do or. And or starts at 0, 1, 2, or 3. So the O is either at the second or third index. So we should be able to do something like this. Section 2 is equal to O, or section 3 is equal to O. So that's 0, O. And that should mean this is an operator equals dot or. Okay. I'm pretty sure I can do the same thing with the rest of them. So that's what I'm going to do. Let's get our semicolon in there. And then I'm going to try to see if I can sort of yank the next 2 lines. So let's do 2y, and then I'll do RP. No, that's not it. P. Oh yeah. Let's do the yanking again. 2 yank, and then P, P, P. Oh man, it's not doing it correctly. Okay. Okay. Or maybe I'm not being the correct one. This is new for me, guys. So, okay. Let's just work with this. This one will be, instead of not operator, this will be equal to the dot and operator. And in particular, we're looking for A's here. Let's find O and replace with A. And then this will be and. Okay, and this one will be L shift. Op is equal to L shift. And then we're going to do the exact same one for R shift. Okay, very good, very good. And then I think there's one case that I'm missing, but we should be also able to do if else, if it's none of these, it's probably an assign. And the reason I say that is because from the past, I think there is one where it's like a big old number. So if it's none of these, if it's not or and L shift right shift, then I know for a fact it's going to be an assign. Whew. All right. So I think we have the operator done. What is next? We now have to parse out the left-hand side and the right-hand side of the expression. And because we did the lower level stuff, I think this part should be pretty easy. So we're trying to parse out this side and that side of the expression. And what we can do is, can we just switch on it? Or do I want to, you know what? I'm going to stick with the ifs. I feel like that's going to be simpler. Okay, so if op is assign, if we're doing assigns, then we know that the left-hand side is going to be basically the whole section. Like we saw it for B, but also for this A example, like you can see the whole section, the whole thing is going to be the I guess the variable. So what we're going to do is we're going to try as any. Because we saw a variable and we saw a number. So we can use as any for that. And then for the right hand side, that we can ignore completely because this is a unary operator. So we can do as int literal, and then we'll just put 0 in there. And basically, do I dare? Let's do yank, not the sign, but to yank the whole block. Oh, we did it. And we should be able to now just paste. Yeah. Okay, very cool. Paste. Okay, awesome. So assign or, assign, not, or, and we're gonna have left shift and right shift. I think left shift and right shift can be done together, but let's just do two. Let's do two of them just in case. I mean, I don't know. I don't remember doing this last time. But assign, we got that. We got that part. And this one is going to be, what's the next simplest one is not, right? And that's also unary operator. So let's look that up real quick on our input. And not start from 0, 1, 2, 3. So 4 and onward is going to be our label for that. So what we're going to do is section 4 onward. I believe that's correct. And then again, this is unary operator, so we don't have to do anything else. Next one is going to be or, and in the case of or, oh boy, this is a whole lot of work here. So this one is, it looks to me like, I don't see any numbers. I think these are all just keys. Yeah, I don't see any numbers. So these are both keys. And the first one is index 0 to 1. Okay, and the second one, this is also a key. I don't think this one returns a thing. This is also a yeah. All right, I'll fix this later. Okay, I'll fix the formatting later. And this one, when does this start? Okay, so it can start 0, 1, 2, 3, 4, 5. So 5 and onward. If I do 5 and onward, this will have a space, but we're trimming, right? So we don't really care about the space. So we can do 5 and onward. We can do 5 and onward here. And you know what? I'm gonna expected. Okay, we're gonna do that. Let's do Zig format real quick. Error expected return type. Okay, so we can't even dig format unless we get a return type in there. Okay, let's do. Yeah. Let's do evaluate key. And then find close bracket, insert, and then is this going to be a bang void? I think it is. Let's do a bang void on that one. No, it's not a bang void, is it? Okay, let's just do it that way. Okay, and then come on, Zig format. Give me a Zig format. Yeah, there we go. Okay, very good. It is lower. Use of undeclared. Didn't I import that? Oh boy. Let's import that. Const is lower is equal to std. ASCII is lower. Okay, there we go. Okay, and then what are we doing here? We're going back to this one. We're still working on parsing the line. I'm telling you, this is harder than the evaluate key one. Evaluate key one, I think I have a good handle on that one. It's never used. We'll get to that one. So nice and well assigned. Okay, have a. So now is and. Okay, and change inside word and. What does and look like? And G slash and. Oh, there's a 1 here. So it looks like for and it can, I mean, I only ever see 1s, but it looks like it can have at least the left-hand side can have numbers. So we'll leave that as any from 0 to 2. But for this one, I think ASCII is what we need for that one. ASCII, and then, you know, we can do as any for all of them and just call it a day, but I'm trying to save some CPU cycles here, some clock cycles. So let's see if we can do this right. 0, 1, 2, 3, 4, 5, 6. So we want 6 and onward. Okay. And look how nice it is now that we've done the low level ASCII as int sort of thing. Isn't it nice? It's like a pretty cool. It's like a pretty cool experience, like coding once you've done the low level stuff already. Okay, so L shift. How do I go back? Okay, right. Let's do L shift. L shift, R shift. I think they're the same size, right? So we should be able to parse them together. Let's do just shift. And we can see for both of these, left-hand side seems to always be a key and right-hand side seems to always be a number of some kind. So I should be able to, instead of doing as any, we're going to do ASCII for left-hand side, ASCII, and then this is going to be 0 to 2, 0 to 2, and then as any, no, as int, we're going to do as int, aren't we? And this is going to be for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 and onward? Okay, that sounds right to me. Section 9 and onward, we're going to parse it as an int. Okay, and I think we can do those two together, right? So we don't have to redo this code. And let's delete block. Yeah, delete block. Yeah, very good, very good. Oh, okay, very good. And that's all of it. That should be all the parsing that we need to do. We got the operator. Oh, no. Okay, so here's the section. Look, we just did this section. We also have to do this. We need the key. And the way we're going to do that, I think Boolean flag is simplest, isn't it? So we'll have like a var is key type thing here. And we'll set that equal to false. So the first iteration is not the key, so it'll proceed as needed. But then it'll set its key to true for the next iteration. And that's how we know if it's the key iteration or not. All right, and we'll break after this. So how do we do this? Okay, so key is 2 bytes. Huh. Well, can we just use that? I think we can. I think there's an easy way to do this. Let's do key is equal to ASCII section, because we're giving it the whole set. We're getting this section here. Okay, so we're parsing it as a key. This will give us an operand, and then we can just pull out the actual key from this operand, right? Isn't that the easiest way to do it? Yeah, I think so. Yeah. I like it. I like it. This is good. All right, so I think we got everything parsed out here. We got the expression, we got the key, and we're loading it in the thing. Okay, very good. Okay, we're done. We're done with the parsing part of it. Now, the actual nooks and cranny. We have to evaluate the expression. Oh, all right. This is going to be a recursive thing. So how do we want to do this? Why do we want to do this? Okay, so let's do a const right-hand side. First of all, this can't return a bang void. This cannot return a bang void at all. We can do a bang U16, but I don't want an operand coming out of here. Okay, I want the actual 16-bit value of the wire. That's the whole point of this function. Okay, it might be able to throw an error, but that's a bubble up error from working with the map. But I want to be working with hard U16 values. And the way we're going to do it, well, let's not do this yet. Let's not do it. First thing we're going to do is we are going to pull the expression out of the lookup. Get key. And I just am wondering, what the hell is this? What does this return? An optional value. So optional expression is what I'm getting back. So let's do const expr, and then it better not be an optional, man, because the key is given to me. They're saying check for key A, right? So I'm comfortable. So just so you guys know what this dot question mark thing is, it's an alias for or else unreachable, meaning that if this thing happens to be null, it will execute this block of code. And whenever Zig executes an unreachable block of code, it just sort of panics and exits, right? And that's exactly the behavior I want. Because if it's null, that means advent of code messed up. That's not me or anything like that. So let's pull out the expression. Now, an expression does have a value. So let's look up the value of that expression first. Expr.value, which is null by default, but if it's not equal to null, that means we've evaluated this expression before, and we can sort of return that expression's value without much other ado, right? That should make sense to everybody. But then if that value, if it has not been evaluated, we have to evaluate it. So we're going to need a right-hand side, which is going to be a U16 for sure. It needs to be a U16 for sure. And we're going to switch on the right-hand side of the expression. Right-hand side of the expression. This is an operand. It can be 2 ASCII bytes, or it could be a U16, right? So we have to handle both of those scenarios. Switch statement's good for that. Why does it keep doing that? Okay. And we're gonna switch on dot. So if it's a number, that's great. That's great. I will. Can I do this? I'll just take that number out. Is that possible? Let me just check real quick. Yeah, I think it is. We'll just take that value right out. It's great. But if it's a key, we're going to have to do a recursive call, right? So we're going to have to do evaluate key. We have to pull the value. Evaluate key value, and then we can send up the lookup, which is a reference. It's a pointer to a map, right? So we should be able to do something like this. And so it says try. It says I think I might need to try it because I have a bang U16 here. So let's try. Let's try it. And then we have to do the same for the right-hand side. So let's see if I can do yank block. Yeah, yank block. Okay, and then we'll just paste it down here. This is exactly the same thing that I'm doing for the right-hand side. So find R, and then replace L. Okay, very good. Exactly the same thing. So now by this point in the code, we should have a right-hand side and a left-hand side U16 fully evaluated, ready to go. Ready to go, okay? So what next? Next is we have to apply our operator to the U16 values, to our integer values. And the way we're going to do that, we're going to get a result going, and that result must also be a U16. And we're going to switch on the operator, expr.op. And here, I should be able to sort of apply the stuff. So let's just apply the stuff, right? So this is just going to be, we're just going to return the left hand side. That's what assign is basically. And then for not, we are going to do not left hand side. That's also a unary operator. For and, the way you do that is left hand side and right hand side. And for or I think it's just one, right? It's not this, it's just this. Left shift. Okay, so this one is kind of, I remember reading in the Zig docs that you have to incast the right hand side, but I'm not sure why. Is it because, okay, let's just incast it. Let me think it through. Incast right hand side. Oh, okay, yeah, no, it makes perfect sense. So these are U16 values, right? So it's anywhere from 0 to 65,000 something, okay? But it's only 16 bits. The right-hand side also 16 bits. So what does it mean to left shift a 16-bit value 30,000 times, right? Doesn't make much sense. So what incast is going to do is it's going to cast this 16-bit integer into like a log base 2 of 16 of however many bits are in the left-hand side. That's what it, I think that's why they're doing it. So makes perfect sense. I like it. Let's just keep that going. And then left-hand side, and we're gonna right shift. How do you write it? This way, yeah. And this needs to be in cast as well. Okay, very good. And then finally, we're gonna, now that we have the result, let's do expr.value, because now that we have the value, let's go ahead and put it in the expression. I think we don't have to do this because pointers maybe, but I'm gonna do it anyways because I think I've dereferenced it. I'm using get instead of get pointer. So let's just put it back. Let's just put it back just in case, we don't know, and then we'll return the result. Okay, very good. Okay, 16-bit value. Okay, we can learn something from this. So this is recursion. What is the base case? Does this seem like the base case to you guys? If you answered yes, that this is the base case, no, that is not the base case. The base case is actually this guy right here mixed with assign. So assign with a number means that we're not doing a recursive call, right? So at some point in this entire list of instructions, there's an instruction that does not require us to do a recursive call. That's going to be our base case. This guy right up here, this is memoization. And if you've not done this, if you don't know what memoization is, let's see, do we have, yeah, I did pull this up earlier. And what memoization does is it caches the result of a computation so that when you call that same function again with the same arguments, instead of recomputing, it's going to just do a cache hit and just pull out. Maybe cache hit is the wrong word. It's going to just reference a lookup table and just pull out the result of the computation without actually doing the computation. And here is a very good example. So this is Fibonacci. It's implemented recursively, and if you call this on on the number 6, you can see that you're calling Fibonacci 2, Fibonacci 2, Fibonacci 3, Fibonacci 2. You're doing a lot of repeat computations. If you go down here to the memoized version of the exact same function, so this is the exact same recursive implementation of the function, but now we're adding this memo to it. What's happening here is the first time you call the function, it will actually do the compute and then store the actual output of that compute into this mycache object, and then it will return that the result of that computation. Now, the next time you call the same function with the same arguments, it will first check the object, and if the result of that computation is already been cached in that object, it's just going to return that instead of having to run the function again. Does that make sense? That's called memoization. That's what we're doing up here. And that's what that is. So, and the base case for us is assigned to a number, right? So if this function fails, it's because our input is bad, basically. Okay. All right. So let's go back down to our high level. I think we decided to return bang void here. So let's just put a try. And then we will come over here and then we'll do like watch exact this one. File close. Okay, expected error union type found void. So defer try file.close. Well, what did I do there? Vims. Okay. So let's see here. Oh, it's supposed to be defer. Okay, so let me just defer that. And then save. What's the next one? As int should have a try on it. Yeah. Okay. So as int. And then let's go to that one. As in literal is fine. As int. Okay. Okay, that should do it. Okay, dot value cannot assign to constant. Oh, it's just a var type thing? Guys, one more thing I want you to take away from this. Errors are your friend, okay? Like some people get really flustered when they see errors. Don't do that, okay? That's really cringy. Okay, errors are your friend. They're here to help you. And if you didn't have them, you'd be in way bigger trouble. I promise you that. If it was just a cryptic fail, okay, very good. Okay, so now let's run this function. The number that we're expecting here is 3176. I don't even know if that's gonna work. Okay, that is not the number that we were expecting at all, right? So let's just go in there and figure that out. Okay, I'm gonna do some debugging, guys. I'll be right back. So apparently I modified the input file at some point. So what I did was I went back over here, I recopy pasted that over, and now if I do sol, you get the right number, basically. 3176. So yeah, that matches. So the next thing that they have us, they want us to do is take the signal you get from wire A, override wire B to that signal, and reset the other wires, including wire A. What is the new signal that is ultimately provided to wire A? Okay, so let's go in and we'll do that part of it. Vim sol.sig. And for this one, we're going to need one more function, which is going to be the reset function. Okay, let's come down here. So let's do fun reset data. And then this will take a lookup table, which is also a pointer to a map of key expression. Key expression. And the way we're going to do it is, I think, do you want to dereference? I don't think so. I don't think so. Look up dot, look up that get pointer? Nope. No. There's got to be a thing, right? Let's just very quickly. There's got to be a thing. So this is let's go to the definition here. Let's do pub fun. And we'll just scroll through here. Like one of these is iterator. Right? Okay, iterator. Here we go. Here, this is the iterator. We're going to get an iterator from it. Key iterator. We don't need that. We're going to now go to the definition here. And then this is going to give us this iterator object. Just setting HM on it. What the hell is the iterator object? Okay, what is this giving us exactly? It's giving us an entry. What is an entry? Oh, look, it's just pointers. Pointers to the key and then pointer to a value. Okay, that's cool. I can work with that. Okay, let's get the iterator. Okay. Let's get the iterator here, and this will be a var. I'm working with iterators, just with var just in case. And then while we're going to say iterator.next, this should give us an entry. So entry dot value pointer dot. So this is going to be an expression, right? Value is equal to null. Is that correct? I am not sure whatsoever. I don't think I've done this before. Yeah, we're going to go with that for now. Okay, let's just see what error pops up. Expected a return type found this. So this should be a void. This should be just a straight up void. Okay, very good. So now we have an a value. What we're going to do, let's yank this line. I'm going to paste this line down here because we're going to need it in just a second. Let's reset the data. And I'm going to send lookup into there. And then we are going to do lookup dot get pointer for B. I'm going to get the pointer for B. And now the pointer should be a, oh, shit, I have to check the docs for this one too. This is going to give me a optional pointer to a value. Okay, very good. Okay, so we have an optional pointer, so let's, or else unreachable that, and then we're gonna, in particular, access the value and set that to null. I think that's correct. Okay. Oh, no, not set it to null. We're setting it to the value of A, right? Okay, cool. Okay, so now we can rerun this entire affair, but with B. Okay, so let's do B value, and then we'll also replace this to, no, they do want the A value, but they want the new A value, right? Oh my God, I'm jinxing myself pretty bad, but I think this is correct. let me just double check here. Let me just make sure. So override the signal in the B wire. We've done that. Reset the data in the other wires. Done that. What is the new signal that is ultimately provided to wire A? Okay, yeah, I'm ready. I'm right. Okay, very good. So this should be correct. This should be correct, guys. So let's now compile. And then if I run, yeah, okay, I think this is right. This is right. Let's just double check. This is just double check. Yeah, there we go. Okay, very cool. Very cool. So I hope you guys enjoyed this one. I will try to put this code in the paste bin down below, but this is definitely was a fun one to try. And if you are a senior in college, you should be able to do this on your own. Okay, not hard whatsoever. Anyways, thank you very much, guys. Have a great day.